Hi everyone, this is Professor Moser. I just wanted to go over the Exam 1 practice test together for Math 120 that'll hopefully help everybody out and get you ready for the exam that's coming up. So this first exam is going to cover chapters 1 and 2, which is on the Introduction to Statistics as well as Descriptive Statistics. The very first few questions we begin with come from chapter 1, where we have a lot of the popular definitions that are going to be present in this class. In question 1, we were asked to identify the population and the sample of the study. It says a survey of 1,378 American households found that 27% of the households own a computer. Remember, the difference between a population and a sample is the population consists of all of the objects that are being studied, whereas a sample is a subset of the population. So if it helps, you can think sample means some, whereas population is all of them. So here, the study that's actually being done is on American households. So the population would be all American households, and the sample would be those 1,378 households that were actually selected. Okay. There is a little bit of noise in this question, and that's kind of brought out by the number 27. This is neither the population or the sample. This is a describing number that talks about a certain quality of those 1,378 homes that were sampled. We'll come to this later, but that's going to be referred to as a statistic because it's a number that describes a sample. Okay, so be very careful. Don't let that extra number throw you off. Population is all things under consideration. The sample is just a subset from the population. Speaking of which, in question number 2, we were asked to determine whether the value given is a parameter or a statistic. The easiest way to decipher between these two quantities is to consider the start of each word. For example, parameters, these are things that describe a population. So we know that parameters are things that describe populations, whereas statistics are numbers that describe samples. So the two P words go together, the two S words go together. Parameters describe populations, whereas statistics are the same representative quantities that represent samples. Here it says a recent survey of the alumni of a major university indicated that the average salary of $10,500 of its 175,000 graduates was $95,000. So if the question is about whether the number is a parameter or statistic, all we need to determine is, well, is that number describing the population or describing the sample? Here, this was a sample of all of the graduates from this major university. Because that $95,000 is describing the sample, that means that it's going to be a statistic. So that one should be a statistic. In question 3 and 4, we're asked to determine whether the data described is qualitative or quantitative. So one of these two refers to quality-based measures of data. The other one refers to measures of data that use numerics or numbers. And the easiest way to kind of keep the two in check is to break apart the roots of the words. When you see the word qualitative, like quality, it's describing values using quality, so non-numerical characteristics. Whereas if we look at the word quantitative, like the word quantity, is describing things using counts or numerical descriptors. Here, if they say the number of complaint letters received by the USPS in a given day, that would be a numerical value, which would make it quantitative data. The colors of the automobiles on a used car lot could include things like white, silver, gray, maroon, etc. Because those are describing the cars in a non-numerical kind of fashion, the colors would represent qualitative data because they're descriptive only. The next set of questions we get into discusses what type of data collection method should we try for each study. In question 5, it says a study where a drug was given to 23 patients and a placebo to another group of 23 patients to determine if the drug has an effect on a patient's illness. So in an experiment, because there is a treatment that's present here, the treatment is that of receiving the actual drug compared to that of receiving a placebo. This would be an example of an experiment. Okay. In an observational study, there is no treatment applied. People just kind of sit back and naturally watch things as they occur. In a simulation, typically these use computer algorithms or computer programs to generate randomizations and trials that do not involve real world situations in terms of the data collection. And surveys are, I think we're all familiar with surveys. These are things where people are asked to respond to a set collection of questions on a information retrieving device, whether it's online or the old school mailers. But this one should be experiment. A study of the salaries of college professors in a particular state. This would most likely be a survey. Okay, there's no treatment, so it's not going to be an experiment. You can't just willingly observe, for the most part, people's salaries. That's not something that's there. It's not simulation because these are actually real salaries of individuals. But in order to kind of collect and gather that data, you would have to, ask or request that information be returned from the different college professors in that particular state. So this would be an example of a survey. The next one says a study to evaluate the success of a new experimental procedure performed on 35 patients at one hospital. Okay. This one might be a little bit more difficult. Let's rule out kind of the one that's not going to make any sense, and that's not going to be a simulation. Okay. These procedures are actually going to be done in the real world, and so this would actually be a situation where we would actually have to go ahead and perform the operation. Okay. So in many ways, it's going to almost kind of behave like an experiment. Okay, but let's kind of come back to this. Okay. It also has some aspects of a census. Okay, but now census, while it is the correct answer given by the textbook, it's a little bit wishy-washy because whenever we talk about a census would include all of the values of the population. So we would have to have information on all of the individuals that would receive this new experimental procedure. Okay? If the new experimental procedure is only done at this one hospital, so if that's the only hospital doing it, and 35 people were the only people that received the treatment, then this would qualify as a census. Okay. However, if the 35 patients in the one hospital weren't the only people that were receiving the new experimental treatment, then it would be more along the lines of kind of an experiment. And in terms of the experiment, what you would have, it would be a control group, which would be those people that are receiving whatever old procedure is being performed to help the patients with whatever affliction or ailment they have. And then kind of the new treatment would be whatever this new procedure is. And so in medical research, what you would have happen there is you would have a comparison between, okay, what is the success rate for the old procedure, or what are we currently doing to patients currently? And then you look at this new experimental procedure, see exactly how it performs on those individuals, and you kind of compare the two. So in that regards, the new experimental procedure, whatever is new about it, could be viewed as the treatment, which could be a case for an experiment. So I would make the case here that if a student answered either B or D on this test, because it's a little bit ambiguous, I would give the correct answer. While it's a weaker answer, I could also see how some people might view it as an observational study, whereas if you're just kind of looking at the patient's post-op and you're observing their symptoms in the recovery, there would be kind of an observational study or part of it that kind of goes with this. But the actual procedure, it shows, or it kind of indicates that something is being done, would really kind of make observational a weak answer. Okay, some students might be able to appropriately campaign for it and reason through why they came up with observational, and I might allow it. But in my opinion, the best answer for this one would be either B, I think, and then D, because it is worded a little bit vaguely. Okay. Bias in question 8 is not something that we really talked about in our class. You can look it up. Whenever you get into like a research design class, or if you go a little bit deeper, or even in a persuasion argument type class, bias is something that's talked about quite a bit. In the next set of questions, we're asked to identify which sampling technique was used in each problem. In the first question, it says an HCTC statistics student interviews whoever is present in class one day to determine the percentage of students that own a car. This is a classic example of convenience sampling because the individual is simply asking those that are nearby or closest to them or in a way that's very easy for them to gather data. If they wanted to do a more honest type of survey or determination of the percentage of students that own a car, ideally they should ask a wider variety of students in statistics classes. Okay, they could ask students that take the class in the morning, afternoons, evenings, those that take it online, those that would perhaps take it at different campuses in the HCTC network, but simply just asking those students in their own class would constitute what's called a convenience sample. In question 10, it says 35 sophomores, 50 juniors, and 37 seniors are randomly selected from 538 sophomores, 448 juniors, and 394 seniors at a certain high school. We are asked to identify what type of sampling this is. This is an example of stratified sampling. And the reason why it's a stratified sampling is we have the students that are broken up according to class year, sophomore, juniors, and seniors. And from each of those strata, we are picking some, but not all of them. So we took some sophomores, some juniors, and some seniors. So that represents stratified sampling. We take some from every group. This is different than perhaps something that's closely related, which would be a cluster sampling, where in a cluster sampling, you also kind of have a division. Oftentimes in practice, it can be geographic, but not necessarily. And what happens in cluster sampling is the population is broken up into groups that are once again called clusters. And what we do is we choose some clusters, but not all clusters. And if a cluster is chosen, then you pick every element or all of the members of that cluster. Okay. So these two, stratified and cluster, are sometimes often confused. The difference is, if you will, a change in quantifiers. For stratified sampling, both of them are going to be groups, but in stratifying sampling, you take some from all groups, but in a cluster sample, you take all from some groups, is the difference. In question 11, it says every fifth person boarding a plane is searched thoroughly. This would be an example of systematic. Anytime you have a process or a formula or an every other, or every third, every fifth type, etc. sampling scheme, this is sampling according to a formula or a system, which makes it a systematic sampling. Question 12 says, based on 12,500 responses from 48,000 questionnaires sent to its alumni, a major university estimated that the annual salary of its alumni was $78,500. So here we have some responses from some questionnaires that were sent out. So we sent out questionnaires to 12,500 of the 48,000 questionnaires. And we want to determine what type of sampling is this. Okay. Again, this is one where I really believe the wording of the question could have been perhaps worded a little more clearly. Because in many ways, if these are the responses from the questionnaires that we're receiving, so if we didn't receive all 48,000 back, and we only received 12,500 back, then that would constitute what's called a convenience sample, because we're only using those values that were people that actually responded to us. It was a convenient results is what we were using here. On the other hand, let's suppose that we received and all 48,000 questionnaires were the ones that we received. If we select, unbiasedly, just randomly select 12,500 from that 48,000 questionnaire, then that would be a random sample. Okay? In my opinion, the wording is a little bit vague, so I would have accepted both random and convenience as an answer to this question. Okay. In question 13, it says the mean IQ score for adults is 100 with a standard deviation of 15. Use the empirical rule to find the percentage of adults with scores between 70 and 130, and assume that the data has a bell-shaped distribution. So again, that bell-shaped distribution, that's what we call a normal distribution. And the empirical rule discusses the way in which the data set is broken down according to a normal distribution. So anytime you have a bell-shaped curve, the highest peak always corresponds to the mean. The empirical rule says that if you go one standard deviation to the left, that's the mean minus sigma, and one standard deviation to the right, so within a band that looks like this, then that would be 68% of all of the data values should lie in that range. If we go for the mean minus 2 standard deviations to the mean plus 2 standard deviations, like this, within that band, you would have 95% of all of the values in your normal distribution. And if we go one more time, if we go 3 standard deviations to the left of the mean and 3 standard deviations to the right of the mean, then that's going to have almost all, or in particular 99.7% of all of the data values will lie within that range. So my advice is, if you read a problem like this and they tell you the mean and they tell you the standard deviation, just kind of go ahead and diagram it out. Here we are told that the mean is 100, so that's the top of our bell-shaped curve, and they say that the standard deviation sigma is 15. So you can add the standard deviation to go to the right, and we do this 3 times. 100 plus 15 is 115. Add 15 again, we would get 130. Add 15 again, and we would get 145. If we subtract going the other way, this would give us 85, 70, and then subtract 15 one more time would give us 55. When we are looking at the range between 70 and 130, that's 2 standard deviations to the left, 2 standard deviations to the right, so it's symmetric. That would be our 95% interval. So we could claim that 95% of all of the values in this normal distribution would be between 70 and 130. The next question we come to is Chebyshevs theorem, which was an insert in the notes. Chebyshevs theorem says that if you have any type of distribution, here the importance is that it does not have to be normal. So the empirical rule, keep this in mind, the empirical rule only ever applies to a bell-shaped, or what we call normal distribution. If you have a distribution that's in general, or even skewed left or skewed right, or something kind of even funkier than that, Chebyshevs rule still applies, and Chebyshevs rule says that the proportion of the data values that lie within k standard deviations of the mean is going to be 1 minus 1 divided by k squared, where k is the number of standard deviations. Okay. So if you want to think of it as sigma, that works too. Here, in this one, it says if the standard deviation is 2.5, what proportion of the data values would be within 2.5 inches of the mean? Excuse me, not 2.5. Excuse me, so k is not sigma, sorry, I misspoke. K is the number of standard deviations. So here, in this example, k is going to be equal to 3. So it's going to be 1 minus 1 over k, which in this case is 3 squared. And if you punch that into a calculator, use order of operations, that would be the fraction 8/9, which as a decimal would be 0.8 repeating, or as a percentage, 88.9%. So we would claim that 88.9% of the values would fall within 3 standard deviations of the mean. The next question we come to is a calculation of a z-score. This is a formula that you do have to memorize for the test. Okay, there's not many formulas you need to memorize for the exam, but the z-score formula is going to be one of them. To calculate a z-score, we do x minus the mean, so you take your score minus the mean and divide it by the standard deviation. If you're using sample data, this is what the z-score formula would look like. If you're using population data, then this is what the formula would look like. But generically speaking, you can also kind of think of it as a pseudo equation. It's just value minus your mean divided by the standard deviation. And if you're going to do this in a calculator, here they tell us that the value is 55, the mean is 58, and the standard deviation is 3. So we're going to go ahead and plug those values in. It should be 55 minus 58 divided by 3. If you're going to do this, make sure you follow the order of operations. You would want to subtract in the numerator first. That will give us a negative 3 up top, and then negative 3 divided by 3 would be negative 1. If you enter this into the calculator, make sure you put parentheses around that numerator. So it would look like this: 55 minus 58 end parenthesis divide by 3. If I don't put that parenthesis there, then it's going to come out wrong. Because what the calculator is going to do is the calculator will simply go ahead and it'll divide the 58 by 3 and then take that answer away from 55. Okay? So you do need to have, whenever you have a fraction, you should have a parenthesis for the numerator and also generally for the denominator if it has more than one term. Okay? So the correct answer here is that particular value, the value of 55, would correspond to a z-score of -1. We talked about in the lecture, by the way, we talked about the significance of a z-score. The z-score is the measure or the number of standard deviations a value is from the mean. In this case, if you think about this, here's a mean of 58. I don't know that this is bell-shaped or not, so I'm not going to draw a bell, but here's 58. And notice that the standard deviation is 3. So if I subtract 3, 58 minus 3 would give me 55. And notice that that's one standard deviation to the left, okay, which is where that value is. In general, the computation of a z-score, the z-score can also kind of tell you where the value lies in relation to the mean. If we have a positive z-score, that corresponds to a value that's greater than the mean. As we saw in this example, if your value is less than the mean, then it should have a negative z-score. And when the value is exactly equal to the mean, then that would have a z-score equal to 0. Okay, so z-score formula is very important. Please make sure you know this one for exam 1. The next thing we get into is actually a little bit of computation work. So now we're kind of moving into that chapter 2 material where we're working on descriptive statistics. Here we're given a data set. There's 30 values altogether. These are speeds in miles per hour. And we're asked to construct a frequency distribution using 6 classes. So one of the things that's important is whenever you're trying to construct a frequency distribution, we will always tell you up front how many classes to use. Okay, there's going to be no guesswork with this. That'll be always stated up front. One of the things, and this is another formula you're going to need to memorize for the test, is how to compute the class width. The class width is found by taking the maximum of the data set, that's the largest value, subtracting the minimum value, and then dividing by the number of classes. Before even doing that, it's a good idea to take your data set and plug it into your calculator because we want to ultimately sort this. So the way that we do that, recall, is you hit the stat button. We want to go ahead and edit and enter our data set. I already pre-entered these, but I just kind of entered them going down. So, going across, so 48, 4, 38, 41, 50. I could scroll all the way down. Eventually we hit 48, and then it wraps back around, 35, etc. Notice that they tell us that there's 30 values here altogether. And when I enter my last value, is this value 33? And notice that the calculator tells me that this is in the 30th position of my L1 list. So it's good to know that at least I did get 30 values in there. So now what I want to do to help us kind of organize this is I'm going to go ahead and do a sort. To do a sort, you can hit stat, instead of hitting edit, I want to do a sort ascending. This will go from smallest to largest, so I hit sort A. And now the next thing we need to do is we need to get our L1 list in there. You can do so a couple different ways. You can either hit the second stat button, which brings up the list menu, and then hit L1 to do enter. Or if you look on the home key, the second 1 key will actually bring up the name for list L1. End parenthesis and hit enter. And the calculator says done. So it's already done the work for us. Now we need to go back and view the list. And there's again 2 ways you can do this. If I go back into stat and edit, I can scroll through and see that all the numbers I entered previously are still there, but now they're listed from smallest to largest. The other thing we can do if you want to view them horizontally is you can put the list name on the home screen by again either doing second list and hitting enter, or by hitting second 1 and then enter. And now that will display our same list horizontally, where you can use the right and left cursor keys in order to scroll through this list. From there, this should make it easy. Once it's sorted, it should make it easier for us to see the small value. The minimum is 33. And if I scroll all the way to the right, we will see that the maximum value is 50. With a class width of, 6 classes, it's going to be 50 minus 33 divided by, there's a typo here, divided by 6. So if I punch this in, it's going to be 50 minus 33 divided by 6. And this would produce a class width of about 2.8. One of the things to keep in mind as it pertains to class width is class width always gets rounded up. It does not follow the standard rounding rules. So here, even if you made a mistake, you would probably still round it up and get the correct answer of 3. Okay. However, whenever it comes to class width, if this had been like 2.1 or 2.3 or even 2.2, you still always bump it up to the next number. Okay. From there, we're now ready to go ahead and fill in our classes. We are going to have 6 classes altogether, 1, 2, 3, 4, 5, 6. And you begin by plotting the minimum number, which is 33. This is what's called the first lower class limit. You then add 3 to uncover the next lower class limit, and just continue to add to go down. So you add the class width to go down. 33 plus 3 would give us 36, plus 3 is 39, plus 3, up until we come to our last lower class limit, which would be 48. The next thing we will then do is work on the upper class limits. So right now, we wouldn't know what this 35 is, but essentially what needs to happen is this class needs to end before the next one starts. So if the second class starts at 36, then that means that the previous class must have ended at one before that, which is 35. And that's how you can find the first upper class limit. Once you have that first upper class limit of 35, you repeat the same thing. You add 3 to go down to get the remaining upper class limits. That produces 38, 41, 44, 47, and 50. Once we have our classes, it's simply just a matter of going through and scrolling through our list and counting up how many of each type shows up. For example, with our sorted list, if I want to look at the first class, how many values do we have in between 33 and 35 inclusive? Well, I have a 33, there's a 35, and then another 35, so that's 3 values altogether for a total of 3. Between 36 and 38, I have 1, 2, 3, 4, 5, 6, and now that would be too much, so there's going to be 6 in there, and then you repeat this and just kind of go ahead and count them all up. Okay. So you do this for every class, and that gives us our frequencies. So it's just a count of how many numbers we have in each class. A quick and good check to do with this is add up all of your frequencies. the sum of all of your frequencies should add up to the total number of numbers we have altogether. If you do 3 plus 6 plus 6 plus 6 plus 3 plus 6, that does add up to 30, which is a good indication that we did the problem correctly. We didn't miss any values, nor did we accidentally double count any values. The other thing we want in our frequency table is the relative frequency. The relative frequency is the ratio of the size of each class to the total data set. And it's found by simply taking the frequency of each class and dividing it by n. So for example, when we know that the first class has a frequency of 3, the relative frequency here would be 3 divided by 30, which is going to give us 0.10. Similarly for class 2, you take its frequency, divide it by 30, that gives us 0.20, etc. You just keep on going. The cumulative frequency, this is a little bit different. This is a running count of the frequency within each class plus all of the frequencies in the classes before it. Whenever we start out, the cumulative frequency of the first class is just equal to that first class frequency. So it's 3 and 3. When we come to the second class cumulative frequency, it's the sum of 6, which is in its class, plus the class before it. 6 plus 3 is where the 9 is coming from. For the third class, we need to do 6 plus 6 plus 3, which would give us 15. And then you just kind of keep repeating this. For the fourth class, you need to add the 6 from that class, plus all of the ones before it. 6 plus 6 plus 6 plus 3 would give us 21. Alternatively, one of the other ways you can do this is to find the next class cumulative frequency. Essentially, all you're doing is adding the current class frequency to the previous class cumulative. So 15 plus 6 would give us 21. 3 plus 21 would give us 24. 6 plus 24 would give us 30. And that's another way you can check. At the end of the day, when you're done with your cumulative frequency, the cumulative frequency for the last class should always be equal to the size of your data set, which in this case is 30. To find the class midpoint, you simply take the lower limit plus the upper limit divided by 2. So 33 plus 35 divided by 2 would give us 34. For the next one, you would do 36 plus 38 divided by 2. That would give us 37. Alternatively, once you get that first class midpoint, you can once again add the class width to go down. So adding 3 is a faster way to get the rest of the midpoints once you have the first one. From here, we could go ahead and do the histogram. For us, we would do our histogram using the class midpoints, would be your horizontal values. The frequency or the relative frequency, depending upon the scale, would be the heights of each bar. And keep in mind, one of the important things when you're doing a histogram, there should be no space between the bars. Wherever one bar or one class stops is immediately where the next bar or the next class picks up. In the next example, we're asked to find mean, median, mode, range, and variance from the sample data. Okay, this is very important. We have to kind of pay attention here. This is sample data. We showed in the lecture how this can be done easily using the TI calculator. So first things first, I need to enter this data values in here. And to do so, I want to go up and I want to clear the list L1. It's very important that to clear the list, you use the clear button, which is right here. I hit clear. It might not look like it did anything, but then if you then move the cursor down off of the list name, it will start with a fresh L1 column. If you make the mistake, and I know a lot of students have done this in the past, if you accidentally hit the delete key, then it will actually take and entirely remove the L1 list from your calculator. We can get that L1 list back into the calculator by going and scrolling over to a blank list name and then hitting second 1. That says name equals to L1. Hit enter, and then that will re-add the list L1 to your to your calculator. Let's go ahead and let's enter these values. So we have 73, 76, 69, 73, 66, 74, 73, 67, 68, and 71. We had 10 values all together. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The powerful command, which is probably the one we're going to use most frequently this semester, is what's called the one variable stat calculation. I hit stat. We move the cursor to the right so we go into the calculate menu. I hit one variable stat, hit enter. And if you're using the TI-84, you want it set up so that the list L1 is under the list menu. And for right now, the frequency list should be blank. We go ahead and hit calculate. And this is what we come up with. X bar represents the mean, which is 71. The median is also down here, but we have to scroll down a little bit to find it. Wherever it says MED, that's the median. That's 72. The calculator will not show us the mode, but we should be able to find that quickly enough. In order to help us find the mode, you might want to sort your list, which we can do. I'm going to go to stat, sort ascending, enter, second 1, end parenthesis, enter. And let me just now kind of go back through my list. I'm going to hit edit, and I can scroll through, and just by looking at it, the number that appears the most is that number 73. It appears three times, which is more than any other number. So just a quick visual inspection tells us the most common value is 73. So that's our mode. Something else that the calculator will not give us up front is the range. You have to remember the formula for the range. Range is high minus low. Or as we called it previously, it's the maximum value minus the minimum value. If we look through our data set, the largest value in this data set was the 76. The smallest value in the data set was 66. And 76 minus 66 would give us a range of 10. For the next value, let's go to stat, calculate, back to that one variable stat calculation menu. The TI calculator will report both a sample standard deviation and a population standard deviation. And this is where notation is important. Remember, S represents the standard deviation of a sample, whereas sigma represents the standard deviation of a population. When we were entering these 10 values into the calculator has no way of knowing whether we're giving it all or just some of the values. So this is where we had to pay close attention. And remember, going back to the beginning of the problem, they told us that this was sample data. So because we have sample data, we want the sample standard deviation, which is S, not sigma. So the sample standard deviation for this one is down here. That's 3.33. And then in order to find the variance, remember the variance, that's S squared. So you would do 3.33 and square it, and that would give us this value. So 3.33, you can either multiply it by itself or there's this x squared key like this, hit enter. To one decimal place, it would round to 11.1. Here they actually don't say how to round it, but I'll give you very specific directions on the test. To get it to be accurate within two places, then ideally you would need to take the standard deviation out a few more spots to account for round off error. I always recommend students take it out either 4 or 5 decimal places, but if I hit enter, then that would be accurate to 2 places and give us the 11.11. One of the things that's not on the exam, something we're not going to really focus our time on, is going to be the Pareto chart information. So on the review sheet, you can totally disregard question 19. The next one we come to is a multiple choice one. It says choose the one alternative that best completes the statements of the above question. Here it says the mean IQ for students in a popular stats class is 110 with a standard deviation of 5. It says use the empirical rule to find the percentage of students with an IQ above 120. Okay. So again, whenever you hear that empirical rule, a lot of students will automatically kind of default, and sometimes it's also referred to as the 68, 95, 99.7% rule. Okay. Again, if it helps, you can kind of draw us out. We know that the mean, they say, is 110. So that's right here. And then typically we mark 3 standard deviations to the right, and we do 3 standard deviations to the left. The standard deviation this time is 5, so I'm going to count in terms of units of 5. 110 plus 5 is 115, plus another 5 is 120, plus another 5 would be 125. If we subtract the standard deviation to go to the left, this would be 105, 100, and then 95. Let's be very specific, though, about what this question is asking. They want to know the percentage of students' IQs that are above 120. Here's 120, and above would be like this. Okay. Keep in mind, again, with the empirical rule, the 68, 95, 99.7 always refer to symmetric intervals about the mean. 1 standard deviation, 2 standard deviations, and 3 standard deviations. If we look at 120, 120 is 2 standard deviations above the mean. So typically we would associate it with this band here, 2 to the right, 2 to the left, would put us squarely in the 95% region, in between those two. But we're not asked for how much is in between, we're asked for how much is above 120. And this is where we need to utilize one of the properties of the normal distribution, and that's that it's symmetric. However much we have in this left tail is equal to however much we have in this right tail. And underneath the entire bar graph, you would have 100%. So if we know that it's 95% in between those two scores, then 100 minus 95 would give us 5%, which means 5% would lie outside of those two, which would be the area that we call in the two tails combined. So 5% would lie in this circle and this circle together, so combined. But if we're looking for just the amount in the one circle, the amount above 120, because it's symmetric, all we need to do is take half of that, and half of 5% would give us 2.5%. From there, in part B, which is a follow-up, it just simply becomes a percent of. If we have 50 students in the class, we know that 2.5% of them have an IQ above 120, so we can actually use that to figure out the count. Percent of, you multiply, change the percent to a decimal, that's 0.025, times by 40, means that in that class of 40 students, we would expect to have one student have an IQ above 120. Let's take a look at the next question. In question 21, we're asked to construct a stem and leaf plot for the data. And one of the important things we talked about whenever we discuss this type of data display is that it's very important to put a key so that people can kind of discern exactly what's going to be in our table here. Here it makes sense to do it such that the stem would be the whole numbers unit, and our leaves is going to be the tenths unit, which would be the decimal portion of the number. To begin, this is going to be an ordered type of display, so we do want to enter our values into the calculator, and now we're going to go ahead and sort them. So I have entered all of these 20 values into the calculator. I now hit the stat button. I'm going to go to sort ascending, hit enter, list L1, so do a second one, hit enter, and now I'm going to just put it on the home screen, second one, enter, and then we can kind of go through and scroll through this. And obviously I have a typo here because 1.5 is not in that data set. Let's see if we can find it. Oh, right off the bat. What was I entering? So we have 12.9 is the first value going from across the road. Then we had what, 12.1, 9.6. This thing went off the rails pretty quickly. So I'm just going to kind of ignore this, but you get the idea. What we want to do, and this is the important part, whenever you're trying to do your stem leaf display, so you're going to do a sort on this. Let me resort these values. So sort A, second 1, parenthesis, enter. Put it on the home screen, second 1, hit enter. One of the things that's important whenever you're doing your stems is we need to identify what is the minimum value and what is the maximum value. Okay, again, I made a mistake here. 9.3 should be in the data set. So the smallest value is 9.3. And if we look through the maximum value is going to be, if I'd entered them correctly, it would have been easier to see, but it's going to be 15.7. So what that means for us is if we're looking at the stems, we need to make sure that we include every stem that will cover our minimum up to our maximum value, which means we need stems from 9 to 15. So that's the first thing we do. We put our stems in decreasing order. Furthermore, we don't want to have any jumps or breaks or gaps. Notice that this data set did not contain any numbers that were in the 14 range. Yet nonetheless, we still leave 14 in our stem category, but there just won't be any leaves that go behind it. From there, you then go ahead and plot the leaf of 3 behind the 9. This would correspond to the data value 9.3, and we put that in our key so everybody knows how we're writing this thing out. We want our leaves to be in order, and this is one of the things that's nice is if you've done a sorted list, you should be able to see this. And again, I made a mistake, but there should be a 9.3. So it goes 3, 6, 6, 7, and then 8 would be the leaves that go behind the stem of 9. Also notice too that if a number gets repeated, very much like what we see for 9.6, how that value is repeated, every time a number is repeated, you once again have to put that leaf down to show exactly how much or how many 9.6s were shown. Okay, so this was our stem leaf plot. Let's take a look at number 22. In question number 22, we're asked to draw a box whisker plot. One of the things that we recall is that a box whisker plot is actually a visual display for what we call the 5-number summary. When we have a data set or a set of numbers, the 5-number summary includes the min, then the first quartile, which we called Q1, the second quartile, Q2, which is synonymous with the median. So Q2 and median are the same. Q3, and then lastly the maximum. So this would be our 5-number summary. It would again start by entering this data into your calculator. So I've gone ahead and done this. I put this in my brand new list L1. So I do stat, edit. All 30 of those values are in there. So we can now do a stat over to calculate. We're going to do a 1-variable stat. Hit enter. And the calculator will actually give us the entire 5-number summary. Under 1-variable stat, all we have to do is scroll down and it starts to list it in order. So the minimum of the data set is 31. The next one would be the first quartile, Q1, that's 56. The second quartile, which is the same thing as Q2, is 72. The third quartile is 83. And then the maximum value of the data set is 99. So that's the 5-number summary. To graphically show this with what's called a box whisker plot, we begin by making a basic number line. Here we need to cover all the way from our min to our max. So the min is 31, the maximum was 99. So roughly speaking, let's start it at 30, and we're going to go up to 100. We then begin by plotting or making a scale. So here we're going to count roughly by tens. You could rule it by 5s if you wanted to. There's no right or wrong way in terms of how you mark off your horizontal line here. But then above the line, we're going to plot each of those 5 values. So the minimum 31 would be roughly here. The first quartile is 56, which is roughly here. The second quartile is 72. The third quartile is 83. And then lastly, the maximum is 100. So we have a dot plot so far. We have our 5 numbers. And here's how we make the box whisker plot. The box goes around the quartiles. So from Q1 all the way up to Q3 is where our box goes. Somewhere within that box, we'll see the location of where Q2 is. We draw a line through it to kind of highlight it. And then the whiskers themselves extend out from the box to the min and extend out from the box to the maximum. Okay, so that is our 5-number summary. 23 I'm going to skip because in essence we've already kind of talked about this. In 23 we just get some more practice doing a z-score calculation. Again, for the exam, please make sure you know the z-score formula. Z is equal to the value minus the mean divided by the standard deviation. Okay, that's the z-score formula. The last question that's on the exam discusses about which test did a student have a better relative performance on. Here we're looking at a history test versus a physics test. 2 entirely very different subjects and 2 exams that might have been different in nature or even on total score potential. But the way to compare them is to compare them as z-scores. You would compute the z-score for the history test, compute the z-score for the physics test, and whichever one had the higher z-score would be the test on which the student did better. For example, if we look at the history test, the mean for the class was a 79, and the standard deviation was a 4.5, and the student got an 83 in history. So to compute their z-score, you would do value 83 minus the mean of 79 divided by the standard deviation of 4.5, and that would produce a z-score of 0.89 for the history test. If we look at the physics exam, the student received an 84, so that was their score. That particular test had a mean of 69 and a standard deviation of 3.7. So again, it's value 84 minus the mean 69 divided by the standard deviation 3.7, and that would produce a z-score of 4.05. As the z-score for physics was better, we would conclude that the student performed much better on the physics exam. I hope this helps everybody. If you have any questions between now and exam 1, please let me know. Good luck studying. As always, if you have any questions, just reach out, okay?